Hello friends, so let us resume our discussion on the von Mises criteria. So in the previous lecture, we began by considering a triaxial loading condition. So this triaxial loading condition we expressed as sigma 1, sigma 2 and sigma 3. So we began the discussion with, or we largely based our discussion on the triaxial loading condition because the expressions that we derived for the triaxial loading conditions then subsequently can be made specific to any mechanical conditions. So once you have a generalized expression that is based on the triaxial loading condition, based on that you could arrive at any specific loading conditions. So expressions for any specific loading condition, be it uniaxial, be it biaxial or plane stress conditions. So for all these conditions, when you have a set of expressions that is based on the generalized or the triaxial loading condition, you can relatively extract the relative relations based on this generalized expression, and that is the reason why we began our discussion with the triaxial loading condition. So this offers a generalized set of expressions. The other important thing that we looked into in the previous lecture is that it's based on the notations, that is whenever we have the subscript 1, 2 and 3, it denotes the stress conditions that we impose on the material. So this is different from the stress condition that the materials experiences within. So whenever we want to talk about the mechanical condition that we want to impose, the subscript would be of the form 1, 2 and 3. When we want to talk about the stress that is experienced by the material or within it, then we dissociate these stresses into different components and then it would be of this form. We would have specific importance or significance to the subscript. It will represent direction, and in case of shear stress, it will represent plane and direction. So we have to differentiate the stress that the material experiences within it to the stress that we impose on the material. So when you have a triaxial loading condition of sigma 1, 2 and 3, we saw this mechanical condition offers or changes the material or affects the material in two different ways. One is it changes the volume of the material, the other it affects the shape of the material. So one, it changes the volume of the material, the other it affects the shape of the material. Now based on our fundamental understanding of plastic deformation, since we have defined the plastic deformation as the movement of atoms from one equilibrium position to other equilibrium position, we have deemed that plastic deformation is not accompanied by a change in the volume in general case. In general cases, the plastic deformation is not accompanied by, it is not associated with the change in the volume. Now, our aim is to then arrive at an yield criteria that is exclusively for the plastic deformation. So, since one effect of the stress is to render a change in the volume, and since change in the volume is not a part of the plastic deformation but it is the part of the elastic deformation, we have to get rid of that effect of the stress. So one effect of the stress is to change in the volume, thereby it gives or it renders an elasticity or elastic deformation to the material. Our aim is to arrive at a criteria that differentiate elastic from the plastic deformation of the material. So therefore, any influence of the stresses that brings about the elastic deformation of the material should be removed, and therefore the contribution of the stress that brings about the change in the volume needs to be removed. And this component of stress that brings about the change in the volume, we refer to it as the hydrostatic stress or the mean stress, sometimes also referred to as the dilatation stress. Now this stress, it brings about the change, or it wants to bring about a change in the volume of the material, and therefore whatever contribution that it makes, it offers is along the plastic region. Now the other contribution of the stress, the combined or the cumulative or combined contribution of these three stresses is to bring a change in the shape. So this we refer to as the deviatoric stress, and it is of this form. So this stress alone, or this contribution or this effect of the stress alone, brings about the plastic deformation. Now, so therefore when you want to arrive at an expression or a criteria, then it should largely be based on the deviatoric stress, not the hydrostatic or dilatation stress, because this is the only contribution that brings about the plastic change. So now the stress experienced by or within the material when you have a triaxial loading condition like this, when you impose a triaxial loading condition, the stress experienced within the material, it comprises of 9 components. So each would render 1 normal component and 2 shear components. So ultimately you would have 9 components, and of this we saw there are 6 independent components. So the overall stress that acts within the material can be written in the matrix form something like this, wherein you would have your normal components occupying the diagonal elements and then your shear components respectively occupying a non-diagonal positions. So I don't intend to write on everything here, so this is just to give you an idea what other positions will be. So these are not empty, but you can fill it out. So the mechanical condition or the triaxial mechanical condition, it imposes definite stresses within the material, and that stresses within the material comprises of 9 components, and they are expressed in the form of the matrix. So this is the stress that is experienced within the material when you impose it to a triaxial loading condition. Now this overall stress, like we said, comprises of the contribution, or that is of the hydrostatic nature that brings about the change in volume, and a deviatory contribution that brings about the change in shape. We now want to arrive at an expression that exclusively deals with the deviatory components of the stress, and thereby you bring this here. So this is nothing but the difference between the overall stress experienced within the material, and you remove the contribution from the hydrostatic or mean stress. So we saw in the previous lecture, this hydrostatic or the mean stress is the product of the identity vector of the same order of the other stress component or other stress contribution, and 1/3 summation of sigma x plus sigma y plus sigma z. So all these are represented as a matrices. So this hydrostatic stress is nothing but the identity matrix into the scalar value here. So when you do that, you will arrive at a expression for the deviatoric stress, which is again a matrix, but we are interested in extracting a scalar from this matrix. We want to have a definite criterion, and that criterion, in order to arrive at that criteria, we consider the invariant of this matrix. So what this invariant mean is, the criteria should not be dependent on the directions. So we want to have a criteria that is independent of this direction. So therefore we consider the invariant of this deviatory stress matrix. So when we want to consider, the way we could arrive at the invariant of the deviatory stress matrix is the same way you would arrive at eigenvalues and eigenvectors. So when you follow the same approach, you will end up with the invariant of this deviatoric stress matrix. Now based on this invariant of the deviatoric stress matrix, we can postulate a criterion, and that is what is done in the von Mises criterion. So in von Mises, you differentiate the contribution of stress into hydrostatic and deviatoric, and in deviatoric you calculate the invariant values or the invariant expression of it, and based on the invariant component of the deviatoric stress, you arrive at a criterion. So that is what is referred to as the von Mises criteria. So this is just a recollection of what we saw in the previous lecture. So since this is something, my assumption is this something that is new to some of you, and that is why I am rendering a recollection here. So now the von Mises criteria, it states that the invariant of the deviatoric matrix should be equal to a square of a constant. So this invariant of the deviatoric stress matrix, let's begin by considering the invariant for sigma 1 and sigma 2 and sigma 3. This is how we began in the previous lecture, and we saw that this J2 is nothing but 1 by, or rather let me first write, so 1/6 of sigma 1 minus sigma 2 the whole square plus sigma 2 minus sigma 3 the whole square plus sigma 3 minus sigma 1 the square. So this is the expression for the invariant of the deviatoric matrix based on the stresses that we impose. So based on the stresses that we impose, this is the expression for the invariant of the deviatoric matrix. Again, this does not involve the components of stress which act within the material. So this is the invariant for the stresses that we impose. Now we have a constant here. We have to find the value of what that constant is or what that constant relates to. So for that we assume a uniaxial condition wherein along the stress 1 or sigma 1 is equal to the yield stress and sigma 2 and sigma 3 are equal to 0. So when you do that and when you arrive at an expression for K and if using this condition you arrive at an expression for K. So this we all did in the previous lecture, and when you substitute here, then you would end up with an expression that looks something like this. Sigma y is equal to, so this here is the yield strength or the yield stress. This is not, we have a bar here to differentiate it from the stress that is acting along the y direction. So this is nothing but the yield point. So this, when you calculate the value of K from the uniaxial tensile condition, or that is condition that is mentioned here, and substitute the expression here, then you would end up with a description for the yield stress in this manner, for the triaxial loading condition in this manner. Sigma 1 minus sigma 2 the whole square, sigma 2 minus sigma 3 the whole square plus sigma 3 minus sigma 1 the whole square, the whole power 1 by 2. So this is the expression that we arrived in the previous lecture for the yield stress under or based on the triaxial stress that we impose on the material. Again, these are not the components, these are the triaxial stress that we impose on the material. Now, when the combination of the triaxial stresses, when these combinations of the triaxial stresses are greater than your yield point, then your material would begin to deform plastically. So this is what we mean by the von Mises criteria. When this combination of the stresses that we impose on the material, when they are greater than that of the yield point of the material, then the plastic deformation will begin to occur, and that is what we refer to as the von Mises criterion. Now we can translate these, change these stresses that we impose on the material to the components of the stresses that the material experiences, and this again we have seen, we have done that in the previous lecture. So let me just write down the expression, the resulting expression. It will look something like this: sigma x minus sigma y the whole square plus sigma y minus sigma z the whole square plus sigma z minus sigma x the whole square. Again, this is not a matrix, we have a continuing plus here, 6 of tau xy plus square plus tau yz square plus tau z x square, and again this whole power 1 by 2. So we have, instead of the stress that we impose on the material, we now have an expression based on the stress that the material experiences within it, the components of stresses that the material experiences within it. And now when these combination of the components of the stresses that the material experiences within the system or within the sample, when this combination of the stresses are greater than the yield strength, then your material would begin to deform plastically, and this is what we refer to as the von Mises yield criterion. Now one advantage of this von Mises yield criteria is that it considers the squares of the different combinations. So here or in each of these terms here we have combinations of different components and different stresses, and it considers the square term of each of these combinations. So therefore, irrespective of which stress you assume it to be 1, or irrespective of which stress you assume it to be 2 or 3, since we have the square of these combinations, so you would have the same expressions ultimately. So you have a triaxial condition, then you have to designate one as sigma 1, one as sigma 2, and one as sigma 3. So irrespective of which one you assign it to be 1, 2 or 3, since you have the squared term here, you are free to do that. So your expression will be independent of your designation, which is assumed to be 1 or which is assumed to be 2 or which is assumed to be 3. So it gives a generalized expression that is independent of the designation. Secondly, since we also have a squared term for the shear component of the stresses, you don't have to worry much about the convention or the highly complicated convention in the shear components. So the squared term here will also help you in assuming the highly complicated conventions in the shear component. So all these will be positive. So you don't have to worry about the conventions in the shear components. However, you would have to care about the conventions in the normal components because you have to have a definite interaction within the brackets. So within the brackets, you have to have a definite interaction. For that, you have to consider the conventions for the normal stresses. For the shear stresses, you can of course overlook those conventions because you have a square term here. So this is one major advantage of the von Mises criteria. So von Mises criteria, to sum it up, it considers, so the things that we learn from the von Mises criteria is, we learn about the hydrostatic contribution of the stress, we learn about the deviatory contribution of the stress, and we also learn about the invariant of the deviatory contribution. And based on all this, we arrive at the von Mises criteria. So von Mises criteria, it demands all these, the understanding of all these different contributions of the stresses. Now let us see if there is any other criteria that would help us and identify a specific point beyond which the material would deform plastically. So the von Mises criteria has given us these specific points. So whenever the combination of these the stresses that we apply in this expression or the components that we apply in this expression, whenever these combinations or this expression is greater than that of the yield point of the material, then you would have the plastic deformation of the material. So that is what the von Mises criteria would tell you. Now let us see if there is any other way to arrive at similar criteria which tells us beyond this point the plastic deformation would begin. There is one other criteria that is referred to as the maximum shear criteria. So this is maximum shear criteria. So this is another criteria that is different from that of the von Mises criteria. So this criteria, so verbally stated, is quite simple. Of course, the numerical form of it is also quite straightforward. So according to this one maximum shear criteria, so whenever you have a deformation or whenever you have a condition that exceeds the maximum shear, then your material would begin to deform plastically. So you will establish a criteria that is based on the maximum shear experienced by the material, and based on that you will end up saying that beyond this particular combination of stress, whenever you have a mechanical condition, then the material would begin to deform plastically. So this is based on the shear components of stress. So this whole criteria is based on shear component of stress that acts within the material. So this particular criteria is based on the shear component of stress. This is not exclusively based on to start with, this is not from the outset based on the stress that you impose on the material, rather it is based on the stress that the material experiences within. Now when we want to talk about the stress the material experiences within, then we need to dissociate the stress that we impose into normal stress components and the shear stress components, because the normal stress and the shear stress are the stresses that the material experiences within, irrespective of the external loading condition. We have normal stress component and shear stress component under uniaxial loading. We have normal stress component and shear stress component under biaxial loading, and we also have the same for triaxial loading. So the components, since for the maximum shear stress criteria, we need to consider the components of the stresses, particularly the shear component of the stresses. Now we in the previous lecture have derived different expressions for the shear components of the stresses, and one specifically we derived for biaxial loading condition for a 3D plate. So we assumed a 3D plate of thickness, of unit thickness, that is pointing towards us. So this we did it in the frame of plane stress or understanding the plane stress. So in this framework we consider a 3D plate and the width of the 3D plate is unit and it's pointing towards us, and for this condition under biaxial loading, we arrive at an expression for the shear component of the stress, and that expression looks something like this. The shear component of the stress under these conditions is written as sigma 1 minus sigma 2 by 2 sine 2 theta. We took some time to derive this expression for a 3-dimensional plate experiencing biaxial tensile loading. So now we want to have maximum shear stress. We want to arrive at the maximum shear contribution from this expression. So this is possible when theta is equal to 45 degrees and ultimately this sine term here will become equal to 1. So now the maximum shear stress that is possible would be sigma 1 minus sigma 2 by 2. So this is the maximum shear stress that is possible when you have a biaxial loading condition and within the 3-dimensional plate. Now we need to extract a criteria based on this maximum shear component of the stress that is acting on a biaxial loading condition. So in order to do that, let us, similar to how we did for the von Mises criterion, we will assume a uniaxial condition wherein the stress that you impose is equal to that of the yield stress of the material. The stress that you impose is equal to that of the yield stress of the material. Then in that case, the maximum shear stress in that case experienced by the plate would be sigma y by 2. So under the uniaxial condition, when the load that you are applying is equal to that of the shear stress, or the load that you are applying yields stress that is equal to the shear strength, then the maximum shear stress that is experienced within the material would be of this form. That is 1 by 2 or half of the shear stress. Now we can relate these two and we can arrive at an expression that relates the shear strength to that of the stresses that we impose on the material. So now we have an expression that relates the shear strength to the stresses that we impose on the material. Now this is what is referred to as the maximum shear criterion or the Tresca criterion. So what this criterion states is that whenever you have a biaxial loading condition and the difference in this imposed stress is greater than that of the yield stress of the material, then your material would begin to deform plastically. So that is what this maximum shear stress condition or criterion states. So all that it considers is the difference between the stress that you impose, and it states if the difference is greater than that of the yield stress of the material, then your material would begin to deform plastically. So this is I don't know, maybe much simpler, or numerically of course it is much simpler than the von Mises criteria. In von Mises criteria we have to consider deviatoric stress, we have to consider hydrostatic stress, we have to consider the invariant of these stresses, but this is just consider the difference between the stresses that you impose on the material. When that difference is greater than that of the yield point of the material, then your material will begin to deform plastically. So that is what this maximum shear stress criterion states. Now even though the derivation of the shear stress criterion, it began with the consideration of the components of stress. So we begin this derivation of the shear stress criterion based on the components of stress. We end up with an expression that relates the yield stress to two stresses that we impose. So we began by considering the component of stress that is experienced within the material. However, the resulting expression was based on the stress that we impose on the material. So it is important to note that this criterion is for biaxial loading condition. So for the biaxial loading condition, the yield point is nothing but, or the criteria is nothing, or it's based on entirely the difference between the two loads that we impose, and when the difference between the two loads is greater than the yield point, then your material would begin to deform plastically. So now Let us consider a triaxial loading condition, which is a generalized one. So how would this criteria change under the triaxial loading condition? So this is also quite straightforward in the framework of the Tresca loading condition, because the way we would approach or derive at a criteria for triaxial loading condition is we begin by rearranging it on the order of its magnitude. So if sigma 3 is the least of all the stresses that we impose, then it would be sigma 3, sigma 2 and sigma 1. So we began by arranging it or considering the magnitude of each of the stresses. So rather it should be sigma 3, sigma 2 and sigma 1. So we began by considering the, and for triaxial loading, we began by considering the magnitude of each of the stresses that we impose on the material. So from that we identify the minor stress and the major stress. So this is the major stress and this one is the minor stress. The least one is the minor stress and the maximum one is the major stress. So for triaxial loading condition, the criteria then would be equal to major stress minus minor stress. So this would be the criteria for the triaxial loading condition, and we arrive at this criteria by considering the magnitude of each of these stresses and considering the difference between the major stress and the minor stress. When the difference between the major stress and the minor stress is greater than that of the yield strength of the material, then your material would begin to deform plastically. So what we have ignored is the intermediate stress. So in this Tresca's criterion for triaxial loading condition, we ignore the intermediate stress, and the difference that we consider is between the major stress and minor stress. These are entirely based on the magnitude of the stresses. So what we now have is von Mises criteria, and to be consistent we will also refer to it with the name. So the maximum shear stress criteria is nothing but the Tresca criterion. So the von Mises criteria, it considers the deviatoric stress and the invariant of it. So here it just considers the stress that we impose on the material, and this expression is largely based on the components of stress, and again this expression is based on the stress that we impose on the material. So given the simplicity of the Tresca condition, for practical applications wherein all that you know is the stress that is imposed on the material, and you want to find for the given combination of the stresses will the material plastically deform or not. So for practical applications, people often go for the Tresca criterion. However, when you want to be specific on how the material behaves within and how the response of the material would be at the microscopic scale or at the atomistic scale, then you would have to consider the von Mises criteria, because this is largely based, or this tells you how the material would behave internally. So since we have the contribution of, we can calculate the components of stresses within the material. So based on the von Mises criteria, you will be able to arrive or predict the behavior of the material. So therefore, the simpler or numerically simpler Tresca criterion is used for practical applications, and rather a bit complex von Mises criteria is used for the theoretical purposes and to understand how a material would behave internally. Now let us look again into the von Mises criteria to arrive at a, or to see what are the ways we could represent the relations between or this criteria. So how can we represent this particular criteria? So the von Mises criteria we saw can be represented based on the stresses that we impose. Based on the stresses that we impose, the von Mises criteria can be expressed as the yield strength is equal to 1 by square root of sigma 1 minus sigma 2 the whole square plus sigma 2 minus sigma 3 the whole square plus sigma 3 minus sigma 1 the whole square, and this all to the power of 1 by 2. So this is the expression for the von Mises criterion based on the stress that we impose on the material. Now when we square the both sides, you would end up with the expression something like this, by 2 of sigma 1 minus sigma 2 the whole square minus sigma 3 the whole square, sigma 3 minus sigma 1 the whole square. Now let us consider the biaxial stress. Now if you consider the biaxial loading condition, where you have two stresses that act on the material and the third stress is equal to 0, this relation, it reduces to the yield strength square 1 by 2 sigma 1 minus sigma 2 square plus sigma 2 square plus sigma 1 square. Now you could expand this combination of stresses, and then this would look like sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. So you end up with an expression like this. So based on the von Mises criterion, by considering just a biaxial loading condition, you arrive at a relation like this. Now the yield point of a material is rather a constant. So you can assume that, reasonably assume that the left hand side of this expression as a constant. So if you assume this left hand side of the expression as a constant, so you can rewrite this as sigma 1 square sigma 2 square minus sigma 1 sigma 2. So in this case, now what we have done is, we have two variables sigma 1 and sigma 2, and out of this there is only one independent variable, because we have related these two with respect to a constant. Even though we have two variables here, out of which one is independent, because when you assume the value of one, you can calculate the value of other. So that is the reason why we say out of sigma 1 and sigma 2, one is independent. One of these two is independent, because we have reasonably assumed that the left hand side of the equation is a constant. Now under such an assumption, and after realizing that only one of this variable is a constant, then you can change one of this variable, say sigma 1, and for a constant a you can calculate the value of sigma 2. And by doing so, for changing the value of sigma 1 and calculating the value of sigma 2 for a given constant a, if you plot it in a two-dimensional plot, the result would look something like this. Or I will try to make it as clear as possible. So what you end up having is an ellipse. So of course you can already guess that this has some similarity to the equation of ellipse. So now by considering, so these are variables, and so these are, one is independent, the other is dependent, and now for a given constant a, when you keep on changing the value of one and finding the value of other and plotting it in this two-dimensional graph here, then by combining all these different points, you would end up with an ellipse, and this is called as locus of yield. Locus of yield. So what you have essentially done is, so this is L. So what you have essentially done is, you have reasonably assumed this to be a constant, and you have varied one and found the value of another and plotted it in a two-dimensional graph, and you could see this leads to an ellipse, and you can quantify rather the values of this ellipse. So these ellipse as the geometrical form as a major axis and a minor axis. So now minor axis. So now we have calculated the ellipse. So this ellipse is based on the von Mises criterion, and correspondingly the major axis would have a value of root 2 sigma y, or rather which we assumed it to be a, as a constant, and similarly this would be square root of 2 by 3 sigma y. So when you consider one of these to be an independent variable, the other to be a dependent variable, and then you relate it to that of, or assume this to be a constant, then you end up having an ellipse, and by plotting it on a two-dimensional graph, and the major axis of the ellipse is of this form and the minor axis of this ellipse is of this form. Now, so what we have is, maybe I will draw it in a bigger scale because we have to work on this. So you have your ellipse. So this ellipse is the locus of yield for von Mises criterion. Now we also have an expression for, we arrived at an expression for related, so this is sigma 1 and sigma 2. We have arrived at a similar expression for the maximum shear criterion or Tresca criterion for biaxial loading condition. So this was rather sigma y is equal to 1 minus 2. So when you assume, so this is the condition for the Tresca loading yield criterion. So this would be for Tresca yield criterion for biaxial loading condition. Now under such a condition, you can also assume this to be a constant and keep on varying the values of sigma 1 and sigma 2. So when you do that, you would end up with an expression or a plot that looks something like this. Or rather, maybe we have to replot this in order to include the Tresca criterion as well. So let us try to replot that, wherein it is possible for us to consider the locus of the yield that is rendered by the Tresca criteria and the locus of the yield that is rendered by the von Mises criteria. So we want to consider the locus of the yield that is rendered by the Tresca criterion and the locus of the yield that is rendered by the von Mises criterion. So for that, let us first plot the locus of the yield that is rendered by the von Mises criterion. So hopefully I should get it right. Okay, yeah. So this is what all along I've been trying to draw. I'm really pathetic at that, so I'm sorry about it. So yeah. Yeah, wonderful. So now this is the one in the black. Let us refer to as the this is nothing but the von Mises locus. So the expression that governs that is the one here. So this is based on the equation 1. Now based on the equation 2 that is here, we have to calculate the locus of the Tresca criterion. So that would look rather simple. It would look something like this. So we have to have a straight line joining this, and similarly a straight line here, and we have to have a point, or rather so that should be assumed it to be a straight line, and then you have a straight line. So there is not much overlap here. You have a point of contact here, you have a point of contact here, you have a point of contact here, a point of contact here, a point of contact here, and a point of contact here. So what you essentially have is there is a point of contact. So the red one here is the locus based on Tresca criterion, and yeah, these are straight lines. You can assume that to be straight lines. So the most important thing is you have point of contacts here, 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 and here. So let me try to mark that in blue. So you have a point of contact here, you have a point of contact here, you have a point of contact here, 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 and here. So this point here is minus sigma 1. So this point here is sigma 1. So this point here is sigma 2, this point here is minus sigma 2. So under uniaxial compressive loading or uniaxial tensile loading, the von Mises criteria and the Tresca criterion are equal. So when you consider this point here, this point here, this point here and this point here, these are uniaxial tensile loading or compressive loading. So these points are compressive loading, these two are, when it is positive it is tensile loading, when it is negative it is compressive loading. So uniaxial compressive loading and uniaxial tensile loading, and in these conditions you have von Mises criteria and the Trisca criterion are equal for uniaxial tensile and uniaxial compression. Similarly, when the values of the different criteria, so values of the different stresses that we impose are equal. So this is sigma 1 and this is sigma 2, that is sigma 1 is equal to sigma 2, and this point and sigma 1 or minus sigma 1 is equal to minus sigma 2. So in these 2 points, so again equal compressive loading and equal tensile loading, for biaxial conditions you have an overlap between von Mises and Tresca criterion. So von Mises and Tresca criterion, so the consideration of the locus will tell you, so the locus of yield, it tells us when von Mises and Tresca are equal. So these criteria, when they are equal, can be understood from the locus of yield. Now they are equal, so these two are equal for uniaxial compression and tension and biaxial compression and tension only when sigma, the magnitude of the stresses that we impose, are equal. So the von Mises criteria and the Tresca criteria are equal when you have uniaxial tensile or compressive loading. They are equal in biaxial loading condition as well when the magnitude of the stress that you impose are equal. So they can be both compressive or both tensile. When the magnitude is equal, you have the similar criteria. Both von Mises and the Tresca will render the similar criteria. Now the maximum difference is observed in this region. So let me use this color. The maximum difference is observed in this region, and this region is when sigma 2 is positive and sigma 1 is negative. So this region is when sigma 2 is positive. The maximum difference between von Mises criteria and Tresca criteria is observed when the sigma 2 here in this region you observe that this is when sigma 2 is positive and sigma 1 is negative. So therefore when you have a combination of tensile and compressive stress that you apply. So these are the stress that we impose on the material. You have a combination of tensile and the compressive stress. The magnitude of these are equal, but their directions are different. When their magnitudes are equal, but one is acting as a compressive stress, the other is acting as a tensile stress, then you would have maximum difference. Between von Mises and Tresca criterion. So you have equality between von Mises and Tresca criterion when you have uniaxial loading, and when you have biaxial loading of equal magnitude, be it compressive or tension. So both these should be equal, so entirely compressive or entirely tensile, and the magnitude of the stresses are equal, the stresses that you impose are equal, then you would have identical von Mises and Tresca criterion. But the difference becomes maximum between von Mises and Tresca criterion when you have the combination of tensile and compressive loading, and the magnitude of it is equal but the directions are different. The same can be observed in this region as well. So it's of the same in this region as well. So these are the spots of maximum difference. Now it is observed that the maximum difference, so the maximum difference, when you want to quantify the maximum difference, it is just of, or it is of about 15.15%. So the maximum difference when you want to compare the von Mises and the Tresca criterion, it is of 15.15%, and this happens when you have a combination of tensile and compressive stress. The magnitude of these stresses are equal, only the direction is opposite to one another. So what in this lecture we have seen is, we have revisited the von Mises criteria. We have then looked into a new criteria called Tresca yield criteria that is rather straightforward. It just considers the difference between, in a triaxial condition, it considers the difference between the maximum load and the minor load, and when these combinations are, when this difference is greater than that of the yield point, then the criterion states your material will begin to deform plastically. Now, based on the expression for the von Mises criteria and the Tresca criteria, by considering biaxial loading conditions, we plotted the locus of yield. So based on the locus of yield, sorry for the nature of this diagram, but I hope you are able to understand the theoretical background of it or backup of it. So based on the locus of this yield, for different criteria, you are able to identify spots wherein the both von Mises criteria and the Tresca criteria are equal, are identical. So those spots we identified, and we also identified the other spots where the differences are quite large, and we quantified it to be 15.5%. So with this, we will wind up our discussions on the yield criteria, and from the next lectures onward, we will try to, from next lecture onwards, we will try to move on to understanding the behavior of the material exclusively based on the mechanical condition. So let's see ourselves in the next lecture. Goodbye.